say what, but electromagnetics definitely deserves that treatment. I don't know about thermal, but it would be almost impossible unless we had like at least a 3-page formula.
All right, let's get started with this from current slide. So just as a reminder, for final, you're allowed to bring half a piece of paper with whatever you want in it. I'll still give you the dumb formulas that we usually give you. So, whatever. What was I gonna say? Yeah, let me make sure I'm recording because I do not want to do this again. Okay. So today I'm gonna go over active low pass filters really quick. Then I'm gonna review all of the stuff up to starting from frequency scaling up to where we are now. And then next class, I'm gonna just basically start reviewing from MOSFETs all the way to frequency response. So that's kind of the next two classes. We're basically done. Yay. I think I'm out of energy. Trying to get back in shape for the summer. So I'm like exhausted from running around and moving things around in an aimless kind of way. Also cold working out. Okay, so where were we? Yeah, so we've been talking about filters. First we talked about how to design low pass filters, then how to design high pass filters. And now today we're gonna learn how to design active filters. And then active. And then we're gonna be done. Yeah, so that's basically today's lecture. Active filters are actually very easy to design. So there's two topologies we will study in this class. And one is this one. So if we were to analyze kind of the gain of this circuit, so the ratio of Vin over Vout in the Laplace domain or the transfer function, what you have here is Vn, and then you have Ri in parallel to 1 over Sc, and then you have plus minus ground, and then here you have Ro in parallel to 1 over Sco, and this is Cn. And so just to recollect, you basically have zero current going through here, and you have that the voltage here is equal to the voltage here. And so by applying the nodal equation here, what you're gonna have is 0 minus Vn divided by Ri in parallel to 1 over Sc plus 0 minus Vout divided by Rout in parallel to 1 over Sc out. That has to be equal to 0. And so we're gonna get that Vout over Vn equals negative Ro in parallel to 1 over Sc0, and then Rin in parallel with 1 over Sci. And now I'm just gonna write the correct expressions for this. So this is just 1 over Ri plus Sci divided by 1 over Ro plus Sco, and then all of this has to be multiplied by a negative 1. So is that clear to everyone? So what we observe here is that now, if we look at this circuit in a more strategic kind of way, typically our transfer functions, h of s, look of the form s minus z1, s minus p1, s minus z2, dot, 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 s minus p2, dot, 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 s minus pn, s minus p, or z, and so what we can actually do is just choose this resistance and this capacitance so that we can get whatever zero we would like, and then choose this resistance and this capacitance so that we could get whatever pole we would like. And that's what we're going to call a active filter. So let's just say I want to design an h of s equal to 1 over s plus 1. What would I choose, Ri and Ci?
1 and 0.
Yeah, so basically you choose Ri equals to 1 ohm, and then you can choose Ci equal to 0, so you just don't put a capacitor in the input side. And then to get the 1, you just choose Ro equal to 1 and the capacitance equal to 1. And there you go. Now you have a filter with this h of s. That's what we call an active filter, effectively. So basically, so this circuit here will have a frequency response that looks like this, where Ki is Ci over Co. There should be a negative sign here. And the pole is going to be Ro times Co, and the 0 is going to be Ri times Ci. And so we can basically choose whatever value of, as long as the product of Ro and Co is equal to 1, we can design a circuit with a pole at 0. Is this clear to everyone? Yes, no, maybe? Okay, now let's say instead of wanting to design a circuit that has this transfer function, how would we design a circuit that has this transfer function? So we kind of said that all we needed was to put a 1 ohm and 1 farad capacitor in parallel, and then just a resistor, no capacitor, so 0 farad basically. You just don't put a capacitor there to get this transfer function. There should be a negative sign here, sorry. So how would we be able to get this transfer function? What can we do? Exactly, so we can just basically to this output, connect a 1 resistor, and then put a minus plus, and then we have 1 ohm, and then we have 1 farad, and then this will be our output, V out. So the output of this will be kind of the h of this one. We can call it h1 of s, which is just 1 over s plus 1, which we found in the previous part. And then the output here will be h1 of s times h2 of s, which, since they're identical circuits, is just h1 of s squared, which is just this. And this should be negative, I apologize. So as you can see, we can go from a first order low pass filter to a second order low pass filter by simply adding more stages. Each stage gives us an order, it gives us a single pole and a single 0 that we can design for. So this is our final design. Okay. In an exam, what you're going to have to do is you're either going to be given a multi-stage circuit and you're going to have to figure out the poles or zeros, or you should be able to, if I give you an expression like K1, K, S plus 3, S plus 5, S plus 7, you should be able to design a filter that satisfies that. If you can do that, that's it. That's all you need to know. In the exam, you're only going to be tested on filters with real roots, but do realize that there's kind of a caveat here. If you have a complex root or a complex pole, this topology is not going to get you there. Because remember that when you have a complex pole that really looks like S squared plus 9, or where basically this would be completely imaginary, and so you can't really get a single stage thing like this to give you a response like this. For those, what people will use is what we call the Sallen-Key configuration, which looks like this. So this allows us to implement a second order polynomial in the denominator, which allow any arbitrary second order polynomial in the denominator, which takes care of the case where there's complex poles. So with this topology, which gives you one real pole and one real zero, and this topology, which gives you one complex pole, this allows you to kind of basically design any transfer function that you would ever want to design. And the approach would be the same. So if you have basically that you need something to have a denominator polynomial as squared 3s plus 7, then you're just going to choose 1 over R1 C1 plus 1 over R2 C1 plus 1 minus K R2 C2 equal to 3. So basically you're going to match your resistors and capacitors so that you get the correct coefficient, and then you're going to match your resistors and capacitors so that you get the correct coefficient. Same idea, it's just a little bit more algebra. That's it. There's not much more there. So this configuration will allow you to get any second order type formula. Now, sometimes what we will do is we will just assume that this K factor is 1 to simplify this. So if you choose K equals 1, that would mean that RA and RB, that would mean that RA is 0. So in which case you just replace this with a voltage follower. So this is a simplified Allen-Key configuration, which will have this type of transfer function. And now the things that you would basically need to worry about is this and this. So you get a slightly algebraically simpler circuit that has 4 free parameters. Now, do realize that there are 4 free parameters, but you only care about 2 things, which is kind of the linear coefficient of S and the constant coefficient. And so you pretty much can pick 2 of the parameters however you want, or actually one of the parameters however you want, because if you want to actually design to this, no, you can only pick 2 of the parameters however you want, because if you notice, this expression is equal to this expression. And so you just pick any capacitance 1, any capacitance 2. Once you pick those 2, then you have to choose R1 and R2 so that they satisfy whatever CS you need. Or you could pick R1 and R2 and then choose C1 and C2 so that you get what you need, basically. So that's basically it. Okay, so that's basically active filters. Are there any questions about active filters at this point? It's a very simple topic. So last class, we designed this active filter based on this configuration, and we found that this was our H of S. Let's say we wanted to now, instead of using this Butterworth topology, we wanted to use the Sallen-Key topology. How would we choose R1, R2, C1, C2? So let's just say we decided that we're going to pick R1 and R2 to be 1. How would we choose C1 and C2 for this circuit? So we're going to have that 1 over R1 times R2, C1, C2. Because they told us that R1 and R2 is 1, it's just C1, C2. And then to match this expression, what would that have to be? What does 1 over C1, C2 have to be? Okay, so let's say we're trying to pick capacitances and resistances to match this expression, and we're told that this is the transfer function for this circuit. Huh? Yeah. And then we're also told that we already chose this to be 1 and this to be 1, so we need to figure out what C1 and C2 is. Well, we want this thing to be the same as this thing, so we're just going to set that to 920 squared. And then we also need this thing to be equal to this thing here. So we're going to have that 1 over 1 plus 1 to the negative 1 times C1, which is just 2 over C1. That has to be equal to 920 square root of 2. So what does C1 have to be? Yeah, basically, so C1 equals square root of 2 over 920. And then what would C1 have to be basically for this to work out? I mean C2. So once we plug it back in to here, whoa, okay. Once we plug that back into here, what would that tell us that C2 is? Yeah. So basically C2 would have to be 1 over 920 square root of 2. So that when I multiply them together, I'm going to get 920 squared. Does this make sense to everyone? Okay, so basically, like I said before, this is the transfer function we want. We choose 2 of the lumped elements arbitrarily. We choose whatever we want. And then the other 2 have to be determined to match the transfer function that we designed for. And in this case, basically, that gave us that C1 had to be the square root of 2 over 920, and that C2 had to be 1 over 920 times the square root of 2. Clear? Yes, no, maybe? Okay, so then basically our new transfer function is the same. We're happy. All right, so let's say now, instead of that previous filter, let's say we wanted to design given that we have this low pass filter, let's design an equivalent low pass filter. So if you recollect, this is a voltage divider, so V out over V in is just going to be, so this is SL, so S over 1.5, it's just going to be 1 over S over 1.5 times, or plus 1 times 1, which is just going to give us 1.5 S plus 1.5. Okay, so how would we have to choose R0, Ri, Ci, and Co to give us this transfer function? Let's just assume for a second here that this is non-inverting. So let's just say I connect this now to a voltage follower. So let's say I want to match it, the absolute value of this, not the exact, so that we don't have to worry about this negative sign. So how would I choose R, C, Ri, Ci? Well, how would I choose Ci in order to get the correct transfer function? Yeah, so we need Ci to be 0 because there is no S here. And so we need to get rid of this, so Ci equals 0, so that's an easy one. And then we also need that 1 over Ri is equal to 1.5, which is going to give us that Ri equals 1 over 1.5, which is, 2/3, 2 over 3. And then once we know Ri, now we need to basically figure out what we need this to be. So we can choose CO. What would CO have to be? Yeah, and then RO has to be 1 over 1.5. Yeah, so that's basically it. So that's how we would design our amplifier. Now here, if you notice, I added an extra stage where the gain is just 1 or -1 in order to cancel out the negative sign. So here you're going to get negative this thing, but then you put the second stage to make it positive, and then you're good. All right, so that's basically active filters. That's all you got to know for active filter design. Straightforward stuff. Where's the old or new? Convert to a high pass filter. Let me see. Yeah, let's skip this question because it's kind of complicated. Yeah, let's skip this. Okay. Okay, so that's basically all I had to say about active filters. Does everyone understand active filters? Yeah, any questions about it? It's not a super difficult topic. All right, so that concludes basically this class. That's everything that you need to know for 2K2. Huh?
Have you finally made it?
Yeah, you've made it. So today I'm gonna actually just review the stuff after test 3, and then next class I'm gonna review starting from class 1 up to test 3. So I wanted to make some extra time because this is not really that long of a topic. Okay, so just as a reminder, and we've been actually using this quite a bit for designing filters, so now it actually makes more sense why we care so much about magnitude and frequency scaling. The idea is quite simple, that if you have a circuit and where you have basically R, S, L, or here I'm gonna write it, J omega L, J over omega C negative. If you want to, basically, if you end up with a response H of J omega, once you solve this circuit, and you want to basically now design a circuit that has H of J omega over KF, what you can do is you just replace all of your omegas with omega over KF, and so you're going to get kind of so you're gonna have R J omega L over KF negative J over omega C over KF. And so that gives you a recipe to change the capacitances and inductances so that now your frequency response has been frequency scaled. Because effectively, since you changed everything that was dependent of omega by omega over KF, the relationships would scale, and so you're going to end up with an H of omega over KF. Additionally, if I wanted to multiply this by a constant Km, and the units of this is impedance, meaning volts per current, I just multiply all of the things that are units impedance by Km. So I would multiply this by Km, and then Km, and then Km. So then I get Km. Oh, I should have done it down here. Km, and then Km. And what will happen is that now my transfer function, if it's volts per current, it will be rescaled by a factor Km. If it's current per volts, it gets rescaled by a factor 1 over Km. And if it's unitless, nothing will happen to my transfer function, effectively. And so that's what we called magnitude and frequency scaling. So in particular, to magnitude and frequency scale, we multiply our resistance by the factor that we're magnitude scaling, or Km. We multiply the inductance by the factor Km and divide it by the factor that is frequency being scaled, which is called Kf. And then for the capacitance, we divide by both Km and Kf. And the reason we divide is because if you notice here, capacitance is in the denominator, and so when you multiply impedance, you end up dividing the capacitance. Is this clear to everyone? Yes, no? So that's what we called magnitude and frequency scaling. After we introduced magnitude and frequency scaling, we started talking about filters. In particular, we studied 3 types of filters. There's also a fourth type of filter, which is called the stop band filter, which basically has 0 in the middle and then non-zero at the beginning. So it's kind of like the opposite of this filter, and that would cover all of them, but we don't cover that one in this class, so ignore that. You would do this if you want to block out a certain band in your bandwidth. So if you have an annoying brother or sister, you need one of these, basically. That's why you would want to use one of these things. So that's how it's used in the real world, but we're not going over it in this class. So for a high pass and band pass, when h of j0 equals 0, and then for a low pass and band pass, h of j infinity equals 0. And then what distinguishes the low pass and high pass is that for a low pass, h of j0 is not a 0, and for a high pass, h of j infinity is not 0. So the name is fairly descriptive in the sense that it passes high frequencies. So you expect that the high frequencies would have a non-zero frequency response. A low pass passes low frequency, so you would expect that low frequencies or zero frequency would have a non-zero response. And yeah, that's basically it. And then for a band pass, you just needed to not, for a band of it to be non-zero. Now, do realize that this definition is a little bit wrong, because basically you could have a filter that is 0 everywhere, and that's technically not a band pass, but then it's kind of a trivial filter. So I'm just gonna say that these two things, if both ends are 0, you can assume it's a band pass. Because this is just not an interesting thing. Basically, it's like you're in a dark room. Okay, cool, great. So, but yeah, if this was a math class, that would be an important case. But this is an engineering class, so we're just gonna ignore that. In terms of bandpass filters, we didn't really talk much about designing them, but we did study two topologies, these two. And we said that when you assume that the output was a current and the input was a voltage for the series RLC circuit, that would be a bandpass filter. And when the input is a current and the output is the voltage across the capacitor, that's a bandpass filter for the parallel RLC circuit. Now, do note that if I were to ask you basically plus minus VL, so if I assume that the output is VL, that's not a bandpass filter anymore. Because you have to realize, if this is the transfer function for the current out, the transfer function for VL would need to be multiplied by j omega L, which would give me a square in the numerator. So it would give me two zeros in the numerator and two poles in the denominator, and that's now a high-pass filter. So VL is actually a high-pass filter for the series circuit. And actually, if you look at the capacitor circuit, if I were to look at the voltage across the capacitor, well, that gets multiplied by 1 over j omega c, which will cancel out this j omega dependence in the numerator. And in that case, you actually have that VC for this circuit is actually a low-pass filter. And then the resistor, just for completeness, the voltage across the resistor, well, since that just multiplies by a number, R, that's just gonna still be a bandpass filter. Does what I just said make any sense to all of you, or is this completely like nonsense? Okay. So it's important that you know that the same circuit, if I assume different components of it are the output, I could have, the same circuit could be a low pass or a high pass filter or a band pass filter. It depends on what I choose to be the output, whether it is one or of those. Okay, let's keep going with this. All right, so additionally, we learned some things about this circuit, which is basically that the more damped this circuit is, the bigger the bandwidth, or the more wider this thing is. So as you can see here, if you're undamped, which in this case would mean, so here, series, parallel. Okay, start from the left. If you're overdamped for this circuit, it would mean that the resistance is very high. So R up. For the parallel, it would mean that the resistance is very low. So remember, overdamped means that most of the current is gonna go through the resistor, or in this case, most of the voltage drop will occur over the resistor. So for overdamped, you need that the resistance dominates over the L and C part of the circuit. In that case, you're gonna get very large bandwidth. So for the series resistor, very high bandwidth. If you have a large R, very low bandwidth if you have a small r, and then for the other one, it's the opposite. Now, as r decreases, you're going to get a bigger response here, a bigger peak, a bigger HM. And then in this one, as R increases, you're going to get a bigger HM for the parallel case. And your circuit correspondingly becomes more undamped. Now, for both of these circuits, you should know what the maximum would be. So what's the maximum current we could get out of this circuit? At what frequency would it occur? Yeah, so the maximum you're going to get is 1 over R, and it occurs at resonant frequency, or 1 over the square root of LC, because that is the case where the impedance of the inductor cancels out the impedance of the capacitor. And so all that this source sees is 1 over R, or the resistance. And same thing here, the maximum voltage you can get is I in times R. So HM for this circuit is 1 over R, and HM for this circuit is R. And both of them have a maximum frequency location equal to 1 over LC. These omega low and omega highs, they were derived in some other slide. Big detail, that's a little bit too detailed. One thing that you want to notice here is that intuitively, like I said, you expect bigger bandwidth whenever R is big for this circuit, and so you see that bandwidth is directly proportional to R. And you expect bigger bandwidth when R becomes smaller for the parallel circuit, and hey, look, it's dependent as 1 over R. So even the algebra confirms what we intuitively would have expected. So in an exam, I could give you this plot and tell you this is the circuit, and then I could tell you this is 10 decibels, or let's say 20 decibels. And then I could ask you, like, what is R? And then I could tell you that this is at 1,000. And then I can also give you kind of what the bandwidth is by telling you that this is at 10 and this is at 10,000, let's say. So then you're going to know that basically R over L is equal to 10 to the 4 minus 10. You also know that 1 over the square root of LC is equal to 1,000. And then from the 20 decibels, well, in linear scale, this is 10. So you're going to get that 1 over R equals 10. And so from this, you could, just by looking at this plot and me telling you that this is a series configuration, you should be able to determine RLC. Does that make sense? So as you're studying this bandpass response type stuff, it's very important that you have an idea of how you can extract each of these quantities, omega low, omega high, from the graph, and that you have these formulas, which you're gonna get a formula sheet, so in order so that you can calculate what R, L, and C is. I could also just give you the circuit and tell you, hey, what's HM, what's the bandwidth, what's omega low, omega high. Yeah, so that's kind of what, at the level that you should understand this at this point. Okay, so let's move on to Butterworth filters. Okay, so after we finished talking about bandpass responses, we started talking a little bit more about how to design low-pass filters, and in particular, we defined 4 parameters: H max, which corresponds to A max, and remember that the A's are just 1 over H. So 1 over H is just A. If you divide in the linear scale and the log scale, that turns into a negative sign, and that's why if you write this in dB, A max is just negative H max, and A min is just negative A min, because in the logarithmic, division becomes subtraction, basically. Okay, so we said there would be 4 parameters for our designs: H max, H min, and for H max and H min, there would be an A max and A min that correspond to them. Additionally, we said that there would be a omega p, which defines the pass band, and omega s, which defines the stop band. So for For low pass filters, we need that for all frequencies less than omega p, our response is higher than H max. And for all frequencies greater than omega s, we need that our response is less than H min. To achieve this, what we said is that we were going to start with a filter that had a 3 decibel frequency, or a cutoff frequency, at 1, and we were just going to frequency scale that. And so in order to design these filters, we need to figure out by how much to frequency scale it. And then we also had to figure out what kind of slope we would need in order to make this transition between the frequency response H max and H min rapidly enough. We derived 2 formulas. One was to find the minimum order. Of course, if order 2 works, order 3 will also work, because that's just going to make it better. Order 4 will also work, because it's just going to make things better. So this formula gives you that the minimum order you need to be able to have a steep enough slope to basically make the transition from the pass amount to the stop band amount. And in order to evaluate that, we plugged in A min, A max in decibels. So look, this is a decibel to linear conversion, so you don't have to convert it. That's what really this is. This is taking a quantity in decibels. It's dividing it by 20, and then it's taking it to the 10th power of that. It's not really dividing by 20 because there's a factor of 2 that you get from the formula, but this is a decibel to linear conversion. So remember, you plug it in decibels, you get your number, and then you figure out your order. Once you know your order, then you pick a topology, which is, these are your normalized filters that you can just look up. Once you pick your normalized filter, then you plug in the order you chose along with the design parameters, again in decibels. And that's going to give you how much to frequency scale it, and then you frequency scale your design, and then you're done. That's how we design low-pass filters. Are there questions about this at this point? So designing involves two things: finding N-min, finding omega C, and to find those two things, you just plug in whatever A min, A max, omega P, and omega S is given to you. That's it. Okay, so then once we learned how to design low-pass filters, we started talking about high-pass filters. And we basically said, well, we know how to design low-pass filters. So then we defined a transformation from low to high-pass and from high-pass to low-pass. And so then we said, okay, what we're going to do, if we're given a high-pass filter design, we're going to first convert it to a low-pass filter design problem. We're going to design a low-pass filter. Once we design this low-pass filter, we're just going to convert it back into a high-pass filter via this formula. And that was basically what we did. Is this clear to everyone? Yes? So basically the design went something like this. This is the filter we want. And what we ended up doing is we basically came up with an equivalent design problem for the low-pass filter. And then we designed this filter. And then that filter would, the filter we designed has a frequency response that looks like this. And so we need to basically replace the omega dependence. We need to cancel out this omega p, and we need to take the reciprocal of it. To take the reciprocal, we replace capacitors with inductors and inductors with capacitors. And then in order to get rid of this omega p that we initially multiplied with, we have to frequency scale by omega p, and that makes sure that everything works out. Now, had we, instead of using this, we had basically done this, then we would lose that omega p factor. But that's not what the book did, so we're not gonna do that. Is this clear to everyone? Yes, no, maybe? So that's our Butterworth filter design. So we take our omega S, we find the capital omega S by basically the conversion omega p over omega. And so capital omega S would just be omega p over omega S. Capital omega p would be omega p over omega p, or 1. And capital omega C is just omega p over omega C. Once we have these three parameters, we plug them into our design formula for the low-pass filter, and we design a low-pass filter. Once we design that low-pass filter, we just convert it to a high-pass filter. Is this clear to everyone? Okay. And that basically concludes everything we've done since exam 3. So the roughly half of your final will be this kind of stuff. Yeah. Questions? So you should know how to, if I give you an A max, A min, H max, sorry, or omega S and omega P, you should be able to design a low pass filter, a high pass filter. Now, I might just ask you for what is the minimum order that you need if these are your specs. I might give you an order and ask you to design a filter. I might, instead of asking you what is the minimum order, I might tell you kind of which of these circuits could you use to design this filter, which basically is asking you kind of to determine the order and identify which one is a low-pass filter of that order, if that makes any sense. So you need to know how to use these formulas. Now, what else could I ask you? I could give you kind of the design specs and ask you if it's a low pass or a high pass filter. So you have to realize that for a low pass, omega p is smaller than omega s, and for a high pass, omega p is greater than omega s, because the pass band is at the end for the high pass, and the pass band is at the beginning for the low pass. That's pretty much it. No trick questions, I would say. In terms of the magnitude and frequency scaling, I could ask you to magnitude frequency scale something, and then I could give you a transfer function and ask you how it gets shifted. I could show you two frequency responses, and then based on those frequency responses, you have to guess how a circuit was frequency and magnitude scaled, based on how the frequency responses shifted. And I could even take it one step further and ask you to modify a circuit based on that. So I can tell you that this circuit has such and such transfer function, and I frequency and magnitude scale it, and I got this. What is my new R and what is my new C? So first you have to figure out from the plots what Km and Kf is. Once you figure out what Km and Kf is from the plots, then you just magnitude and frequency scale that circuit.
How do you figure that out?
So you can look at the response at omega equals 1, and then see where this line kind of has that same change, and that's going to give you the factor Kf. And then as for the magnitude scaling, you can look at what Hm is and see how much smaller it is. And depending on the units, if it's volts per current, then that's the Km factor. If it's current per volts, then that would be the 1 over Km factor. We'll go over some examples next class of this kind of stuff. What else is there? So that's for magnitude and frequency scaling. For this, I could give you either an H of S and ask you, is this a high pass, low pass, band pass? I could give you a circuit and ask you, which we went over last class, is this a high pass, low pass, band pass? So that's kind of basically the kind of question you would expect with this. With this, I've kind of given you an idea. I can give you this plot and ask you what RL and C are. I can give you RL and C and ask you what bandwidth or whatever is. I can ask a more interesting question where I say, if I made R bigger, would the bandwidth increase or decrease? Which, of course, if you have this formula, then you'd be like, oh, well, if you make it bigger than bandwidth, then I hope you can get them. And then, that's pretty much it. That's the kinds of questions you should know how to answer. There's some good examples in the previous exams of the things we ask, which doesn't deviate much from what I've just told you. Any other questions?
Did you write the exam yet? Or?
No, I'll write it by Thursday. I've just been really behind this last few weeks. I recommend you study all previous exam questions. A large portion of them will be very similar.
Like on Brightspace, the old exams?
Yeah. You should know all of those very well. A large portion of the exam will be very similar.
Are we still allowed a formula sheet or?
Yeah, half a piece of paper, double-sided. I'm also giving you the normal formulas I give you, so it's oh yeah, before, so someone complained about quiet week. I forgot about this. Yeah, and that we're not allowed to give homework, exams. So we've decided. So I read the policy and it says we're not allowed to give assessments, but we're allowed to give points for participation. So we've posted the solutions to the homework, and the homework is still not due. So technically, you're just asking to participate in submitting the quiz because you already have the answers. Ideally, you do them by yourselves, but we're just asking you to participate in submitting the quiz here. I don't know. And next quiz, it's gonna be basically a makeup quiz, where if you miss the quiz during the semester, you're gonna be able to drop a second quiz, but if you don't wanna take it, you don't have to take it. So I'm gonna drop a total of 2 quizzes, and the 6th quiz will basically be just to boost your grades at this point. If you missed the quiz in the past. So if you don't take it, it's not worth anything, basically. That's the compromise here, or the deal.
Wait, so what is that quiz? Is that?
So next class, we're supposed to have a quiz.
Yeah.
So I'm just gonna drop 2 quizzes instead of 1. So you can choose not to take it, and it's not gonna affect your grade.
What would the quiz be, like if I choose to take it? Because I did miss a quiz this year.
It's the same quiz that you would normally take. It's based on this material I just
Okay,
covered.
So just like filter design practice.
Yeah.
So if we did the self-assessment thing, the assessments, are we going with street quizzes?
No, 2 quizzes I think is good. Yeah. Yeah, so that's basic. So that's basically all the announcements I have. Yeah, I'll see you all later.
Are you good?
Yes.